Hello. In this video, I present our work on anomaly detection using generative models and some product networks in mammography scans. This work was developed at the VR Research Center in Austria in cooperation with Martin Trapp from the Aalto University in Finland. My name is David Major, and I will present our joint work. Developing robust AI-based mammography screening methods to support physicians is an important goal, as breast cancer is the leading cause of death in women. When it comes to training of AI models for the detection of breast cancer in mammograms, the following challenges emerge. There are usually more images from healthy patients than images of cancer patients, and there is a lack of anomaly annotations. Anomaly detection is a good candidate to address these challenges. It requires solely healthy data for learning. Anomalous data can be detected by measuring the deviation from the learned distribution. This way, there is no need for anomaly annotation. State-of-the-art utilizes different autoencoder and GAN variants to solve the anomaly detection task. These methods are well suited to capture the data distribution, but fall short when it comes to inference. They usually apply image reconstruction quality or variational inference to compute anomaly scores, which are merely approximations of likelihood and can be inefficient to derive. For this reason, we propose to combine autoencoders with some product networks, where an encoded latent vector is passed as input to an SPN, which yields a likelihood as the anomaly score. SPNs are probabilistic graphical models with special structural constraints and allow exact and efficient log likelihood inference. They combine three simple concepts. They have simple distributions at the input over subsets of input variables. They join the subsets together by factorization, which are represented by product nodes, and mix the result together by sum nodes. The log likelihood is inferred after the last single sum node in a generative setting. In this work, we utilize the random and tensorized sum product networks, in short RAT-SPNs, introduced by Behartz et al. It has the following features. It constructs a random structure instead of structure learning. If we consider an example with 7 input variables as visible on the right, then a random region graph can be built by splitting up the variables in 2 parts randomly. It is repeated 2 times, resulting in a depth of 2. The graph is populated by 2 leaf distributions, 2 inner sums, and a single root sum in this example, and is finally turned into an SPN. The framework has a tensorized implementation and is compatible with GPU-supported frameworks such as TensorFlow. It is trainable by stochastic expectation maximization for the generative setting. We evaluated 3 autoencoder types: convolutional autoencoders, beta variational autoencoders, and vector quantized variational autoencoders. We trained and evaluated them standalone and in combination with RAT-SPNs. The best fit RAT-SPN parameters were found using grid search on a small set of validation samples. Additionally, we trained and evaluated the state-of-the-art F-anogan approach in its standard configuration. Our training data consisted of 64 by 64 pixel patches from the DDSM collection, and we tested with selections of mass and calcification images from the CBS DDSM set. Here we show our quantitative results. We calculated pixel and image-wise AUCs of anomaly scores at healthy and anomalous pixel positions using pixel-wise ground truth information. It is visible that for the mass set, there is a statistically significant improvement for the convolutional autoencoder and the vector quantized variational autoencoder setups over the standalone assessment. For the calcification set, no statistically significant differences are present. We found that the higher amount of dense breast tissue in this set is responsible for the poorer results. The state-of-the-art F-anogan is outperformed in both sets by a small margin, although not statistically significantly. And finally, here is a visual comparison of the different models. The original image and the anomaly score heat maps are depicted in the first row. The ground truth and the masks generated by the 99th percentile thresholding are illustrated in the second row. Hausdorff distances to ground truth are visible below the method names in brackets. In summary, it is visible that the RAT-SPN extended models generate anomaly score landscapes from which the best anomaly masks can be derived. Thank you for your attention.